So we are still on section 1.5. We are talking about graphs of trig functions. In previous lectures we have talked about graphs of sine, cosine, and tangent. What we want to do today is to talk about the graph of cosecant, secant, and cotangent. Now we have three ways of doing these graphs. One is patiently doing the point plotting. So you make a table of values, give x and y's, and plot them individually. I'm going to leave that to you. Option 2 that we can approach them by is to realize these functions are reciprocals of those functions. So we are going to use reciprocal identities. And essentially learn how to graph reciprocal of another graph. Option 3 is to push our luck and try to get interpretation for these things on the unit circle. So let's see if we can talk about some of them. At least cotangent is going to be easy. These are a little bit harder using unit circle. So these are the objects of the talk today, and perhaps answering some questions, and if we get lucky perhaps we can break into 1.6 and talk about other useful things about sine and cosine. Okay, let's quickly remind ourselves what was the graph of sine. So sine function, we say it has look something like this. Suppose this is 0, this is 360, and then midpoint 180, and midpoint of those 90 and 270, and I have a wave going through these points, and that determines my fundamental cycle. So this is the graph of y is equal to sine of x. Now I am interested in graphing y is equal to cosecant of x. We remember that cosecant is same as 1 over sine. Is that right? Cosecant is 1 over sine. So we say, well, can I use that to get a quick picture instead of reinventing everything from scratch? You say, well, yes. Let's just practice. Suppose you wanted to do point plotting. If suppose you are interested in cosecant of 30 degrees, or what is that? If you wanted to calculate it off of your calculator, you should have had sine of 30 degrees and get the reciprocal of that. Well, you know sine of 30. What's sine of 30? 1/2. So reciprocal of 1/2. What's the reciprocal of 1/2? 2. So okay, if this was 30 and this was so this is 30, this is 1/2. The corresponding picture for cosecant wants me to stand up at 2. Remember, this is 1, so 2 will be somewhere here. Let's see if you understand what happened here. This is the height of sine. Height of cosecant is the reciprocal of height of sine. So if this is 1/2, that has to be a 2. If I was at 1/3, what would be the corresponding point up here? There was an angle whose sine was 1/3. What would be the cosecant of the same angle? The question is, suppose sine of some angle is 1/3. What is the cosecant of the same angle? Say it again. Which is 3. So whatever this one is, the other one is a reciprocal of that. Now as I come close to the origin, what happens? That height gets smaller and smaller. If some number gets smaller and smaller, what happens to its reciprocal? Like I come closer here, suppose the height is 1/4. What's the reciprocal of that? 4. Come closer, this is 5, reciprocal of that, and 5. As I go towards 0, these reciprocals, where do they go? Up to infinity. So that's the issue of asymptote we talked about last time. These points are tending toward infinity. Where this one goes to 0, the other guy goes to infinity. How about that? That's height. Sine of 90 is 1. What is cosecant of 90? 1. So this reciprocal of 1 is just 1. So I come down here, and then again, when this is a half, I go to a 2. When this is a third, I go to 3. When this is a quarter, I go to 4. When it goes to 0, I just escape to infinity. To guide my hand, I draw this line, which I call it a vertical asymptote, and these points just escape to infinity next to that asymptote. We are going to have one of these asymptotes at any point that sine hits the x-axis. So here there's going to be another one. So these green lines just come up, never touch these purple lines. They just go straight up, not to be confused with a parabola or anything, just really shooting up straight. What's going to happen on this negative side? Suppose I had 210 degrees. Sine of that is -1/2. What's the reciprocal of -1/2? -2. So -1 gives you -1. -1/2 gives you -2. -1/3 gives you -3. What happens here is that you get the same picture, but it's just opening downward. And it is limited between these two vertical bars. So what we have here is a graph of y is equal to cosecant of x. That's a nice interruption. Cosecant of x, it looks like this. So notice I didn't keep fumbling with a calculator to get some numbers. If I get the idea, I can do the whole thing in just 10 seconds and even less than that. I didn't rely on anything. That's a lot more pleasant than trying to get numbers, filling up this table, and doing things like that. So you have the graph of sine. You should graph the reciprocal of that. What are the main ideas? Reciprocal of 1 is 1. So at this point I touch. Reciprocal of 0 is infinity. Reciprocal of 0 is infinity. We distinguish between positive 0 and negative 0. That sounds funny, but when you're coming down here, you're going toward 0 while being positive. That means your reciprocal is going to be at plus infinity. When you're down here, you're approaching 0, but you're hovering in the negative territory. So your reciprocal goes to minus infinity. So again, this is like one of those, we talked about that Pac-Man game, that when this creature comes to this end of the screen, as you go up, if your graph is supposed to continue, it is re-emerging at this other end. Okay, so it jumps from plus infinity to minus infinity to continue. It goes to some other word and comes back on the other side. So that's the picture of a cosecant. With that in mind, we can perhaps do secant quickly. Let's see. Maybe you want to do it before I do it. Again, we start with the graph of. So the question is graph y is equal to secant of x. We remember, in this style, we remember secant is 1 over cosine. Okay, if I learn my lesson on cosine and I know that one, I can build my answer off of that instead of doing everything from scratch. So, okay, what is cosine going to look like? Cosine, it started at 1 and 90 degrees hit 0, and then at 180 was minus 1, at 270 it hit 0, at 360 it's back to 1. If you want to go back, here's at minus 90, so minus 90, 0, 90, 180, 270, 360, 450. Then what? You know, each intersection spells a vertical asymptote. So we draw these vertical asymptotes here. Notice how quickly we are doing this. If the software doesn't come in our way. Now what do I do next? Tell me what to do in this section. So what's going to be location of the turning point or the bottom of this piece? X equal to 0 and y equal to 1, is that right? When I hover towards 0 at positive territory, it pulls me all the way up to infinity. Here everything is going to be negative. This negative 0 sends me down to negative infinity. Here, same thing. So y is equal to secant of x. Question? Now, if you wanted to limit yourself to this portion of cosine, then you would have limited yourself to that portion of secant as well. Okay? Notice that the whole thing was done in half a minute if I knew what the cosine is. So once again, at each of these intersections of cosine with the x-axis, this is my x-axis, these are my x-intercepts of cosine. Let's note it down. These are x-intercept of y is equal to cosine of x, such points. What happens to them when you deal with the secant? They become location of vertical asymptotes. So same point becomes where are the vertical asymptotes? At 90, well, wherever you see these purple signs, how can you talk it out mathematically? How would you classify 90, 270, 450, minus 90? How can you throw them all in one bag and describe all of them at the same time? Can you find a trick to single out these numbers? So here are my numbers. Location of vertical asymptotes of y equal to secant of x, 90, 270, 450, and the negative of the same number. So I can actually say plus or minus. So if I was smarter, let me get smarter a little bit. So plus or minus 90. Plus or minus 270, plus or minus 450, and so on we go. Plenty of these vertical asymptotes all over the place. How can you easily characterize all of these numbers? good, divisible by 90, but 180 is not the location of vertical asymptote. Okay, well, that's a good step, but you need to correct it. You said divisible by 90, so let's go factor 90 out of it. You say this is 90 in it, fit in it once. This one fits how many times? 3 times. How many times 90 fit in this one? 5. What is your guess on the next? 7, 9. Who are these guys? No. 9 is not prime. Just odd numbers. So odd multiples of 90. So that's our recipe. Locations of vertical asymptotes of the secant of x are at odd multiples of 90. So these are how did they write that mathematically? You can write it as 90. How do you catch a odd number? This is one way. 2n plus 1, where n is an arbitrary integer. Like n could be 0, 1, 2, 3, any whole number. You plug it here, 2n plus 1 automatically becomes odd and goes through all of these numbers and they're negative. You multiply by 90, that tells you where your vertical asymptote is going to be. Okay, let's move on to the next issue, which is how can you get cotangent? Yes. Next issue is how do you get the graph of cotangent? Again, we are trying to do all of these things first by using reciprocal identities. So suppose I want to have a cotangent of x. Yeah, and I want to connect it to its sister. What's the sister of this one? 1 over tangent of x. The question we are asking, if I know everything about tangent, can I quickly figure out my way around cotangent? And the answer is a big resounding yes. Are we done with the section up here? Okay. Now, do we remember what tangent looked like? That was actually one of the challenging pictures in the previous round that we had. Tangent itself had vertical asymptotes. You remember that one? So let me draw some of the pieces of tangent. Here is how tangent look like. Hopefully by now we have that one mastered. So here's the red one is tangent of x. It doesn't have much of a handle to it. It's like kind of a featureless, okay, inverted S or something. Here where it's vertical asymptote. Now, what we need to practice is how to find the reciprocal of this entity. So we say, here's my tangent. It's approaching to 0. When it approaches to 0, what happens to cotangent? In other words, what's cotangent of 0 or cotangent of a small angle? We just learned that reciprocal of a 0 is what? Reciprocal of 0 is infinity. Okay, so when this one goes towards 0, cotangent has to go towards infinity. On the other hand, when tangent goes to infinity, what happens to cotangent? Or in other words, what's cotangent of 90 degrees? Several problems. One is the lack of practice on the tangent itself, and the second one, a little bit of problem with the arithmetic. Let's try it out. Let's try it out like this, step by step. Suppose I take my 45 degree where tangent is 1. What would be the reciprocal of 1? 1. So I know this point for the blue, I know that. Suppose I arrive at the point on this red curve where my tangent is 2. Okay, here is supposed to be 2. The blue curve has to pass through a certain other point, which is reciprocal of 2. What's the reciprocal of 2? 1/2, is that right? Now, as I go up higher, I'm going to pass through 3. What's the reciprocal of 3? 1/3. So I come down here. I go to 4. Reciprocal of that is 1/4. I go to 5. Reciprocal of that 1/5. 10. Reciprocal is 1/10, and so on. So as this one shoots up to infinity, its reciprocal shrinks towards 0. So that gives me the idea that this graph has to just dive down towards 0. And then what happens? Then on this side, when this is going to minus infinity, the reciprocal of that is going to be negative numbers just like this. That is, I'm going to get the same picture, but on the negative side. Now, as red curve approaches 0, like I'm going through 1, 1/2, 1/3, 1/10, and so on, coming close to 0, what happens to reciprocal of these things? Well, reciprocal of 1 is going to be 1. Reciprocal of 1/2 will be 2. Reciprocal of 1/3 will be 3, and so on. But all of them negative. As I approach 0, but on the negative side, my reciprocal also becomes negative infinity. So what I need here is to make sure this graph dives down. That gets me graph of cotangent of x. So cotangent of x has vertical asymptotes 2. Here is one of them at 0. Next one is at 180. Next one is at 360. Next, down here we have one at minus 180. And if you want to draw more of these blocks, here are graph of cotangent of x. So crucial things in helping us getting these pictures was when tangent went to infinity, cotangent went to 0. We symbolize that by saying when you go to infinity, reciprocal of infinity is 0. It's called extended arithmetic. If you take a number, if I have $1 and divide it to entire humanity, out of my generosity, everybody is going to get close to nothing. So $1 divided by a huge number is going to give you 0. What that means is this tangent going to infinity. Cotangent is reciprocal. Blue is a reciprocal of red. So when red goes to infinity, blue has to go through 0. The other side of the coin is that if you take 0 and have 1 divided by 0, you get infinity. Here you have to be a bit careful. If your 0 is positive, you get positive infinity. If your 0 is negative, meaning you're hovering on the negative neighborhood, you get minus infinity. So reciprocal of 0 could be plus infinity, could be minus infinity. You have to see what flavor your 0 has. So if you kind of practice this extended arithmetic, you can get your pictures faster. Okay. I understand these pictures get to be a little bit complicated, and digesting it might be a little bit hard, but let's try. What we want to do next is a second style of explaining these pictures using unit circle. Okay, so style number 3. Why is it you're looking for this picture? We said you have three ways, either point plotting or taking reciprocal identities, and the third style was using unit circle. Let's go and try these things so that we have all of them available to us. You want to go back and forth between these things to make sure whatever guesses you are making in your problems, you're on the right track. So at the beginning, you remember we said when all else fails, you can just crank up your calculator, pick up some numbers, plot it like that. Then we talked about reciprocal identities just right now. Each of these functions is a reciprocal of each of those functions. That's the approach we took. We had to be careful with the asymptotes. Approach 3 is the idea of unit circle. You might suspect some of these might be a bit complicated. Let's perhaps start with the easiest of these things, which is the last function we considered. Let's say graph y is equal to cotangent of x using unit circle. So again, I changed the order because perhaps this is the easiest to digest, and the other ones need a little bit more fancier footwork. Just out of curiosity, do you remember how we investigated tangent on the unit circle? Where was the location of the tangent axis? So this, we have our unit circle in the regular coordinate system. You remember when we were investigating these functions, this one played the role of the cosine axis. So this one played the role of the sine axis. Where was the tangent axis? You remember that one? Not be reviewing the homework, I guess. Well, it's not explained in this style in the text yet, but anyway, this was your tangent axis. We used that in the lecture last time. Now we have a new thing. We have this line as the cotangent axis. What do you mean? Okay, here's the origin of it. Positive on the right, negative on the left. What do you mean it's a cotangent axis? What we mean is that if I draw an angle, so here's my angle in the so-called standard position. Suppose this is my angle theta. From basic geometry, you know that this angle is also what? These two are, what do you call it? Alternate something something. Is that right? Alternate interior angles. Theta, that would be theta. Is that right? You have two parallel lines, transversal, this angle and that angle are the same. Now, pay attention to the following triangle. Okay, let's just color it all. Cotangent of this angle theta would be ratio of, what was cotangent? Ratio of I was hoping to get a chorus at least on that one, but cotangent was a ratio of, let's try again, adjacent over opposite. We want to have those things at our fingertips. It should take less than 1/10 of a second to answer that, because we are at the foot of Himalayas. Let me tell you like that. We have way to go. Okay, so you want to fasten your seat belts and just get ready to go, because that's what the trigonometry is. Okay, cotangent is a ratio of adjacent to the opposite. Who is your adjacent? Let's color it up. Here is my adjacent. Who is the opposite? Opposite is, okay, in a unit circle, what is the property? What is the length of this opposite now? 1. So we have cooked up this particular picture so that when you take the ratio, it conforms to your what should I say? Can I say couch potato mindset? That here's adjacent, opposite is 1, so when you divide it, you don't have to do anything. Right? You don't want to do anything. Adjacent, here's adjacent. Opposite is 1, so division by 1, it just means that you are going to get your numerator. Wow. How is that going to help you? How it helps you is that this purple line that you look at, that is exactly the cotangent. So if you want to have a visual impression, here I draw some angle. What's the cotangent of it? Immediately you have the answer. Here it is. Just use this length as your yardstick, and then you will have your cotangent. Now, after all of this that I said, suppose I ask you to give a ballpark number for cotangent of the angle I drew. Just looking at that picture, what would you say it is? An approximate answer. 2. Because if this is my 1, remember this is my 0, this is my 1, but this one looks like 2. So you have a quick visual estimate of what is going on with your angle. This is my angle, here's its cotangent. What if I had ended up around here? 3. So let's try it out. That's how it helps you to actually graph it, because you quickly do these things without fumbling with a calculator all the time, pressing those buttons and pressing the wrong buttons and this and that. First of all, it takes a long time. Second, you make a mistake half the time, and then it just doesn't really help. So we say, here's my cotangent axis. All I need to remember is that who's cotangent axis and the location of standard position. So suppose I draw an angle like this. That's my tangent. What is your estimate for cotangent? Let's call that theta number 1. What is cotangent of theta number 1? So we say, okay, this is my 1. About 2, about 3. And this looks like what? Maybe 3.5, maybe 3 point something. Whatever you drew, its cotangent appears to be around 3.5 or something like that. What if I make a tiny angle? So cotangent of, let's make it explicit, tiny angle. Well, you don't have to memorize this stuff. You can see it in your head. Okay, that was 1, 2, 3, perhaps 4, 5, 6, 7, 8 or something. The smaller this gets, the larger that one gets. So cotangent of a tiny angle is a large number. Well, what does that say? That says the following. Suppose I want to draw the cotangent on my, so the question again is draw y is equal to cotangent of x. Okay, I say I want to start from here and draw my picture. I have a small angle here. How big is its cotangent? Large, which means what? Where should my starting point of picture be? Where do I start? At a small x. When x is small, y is very large. What does that tell me about location of my starting point? I have to go all the way up here, is that right? For a tiny x, if this is a small angle, its cotangent is huge. So that means I have to start from here. And when you start at infinity, you have nowhere else to go but to descend. Okay, suppose this is my cotangent, my angle increases. What is the situation here? What angle is this one? Let me help you. What angle is in this square? This is 45 degrees, so its cotangent is going to be 1. So we are marching toward 90 degrees. So at 45, we are supposed to get 1. Now I increase my angle toward 90 degrees. What happens when I hit 90? What happens to cotangent? 0. Remember, this is what you are measuring. Like at the beginning it was this big, then it gets smaller, then gets smaller, then gets smaller. This, when you hit 90, your cotangent has become 0. What does that mean? Here are the main points of your picture. At 45 we passed through 1. At 90 we had to hit 0. What if I go to the second quadrant? What happens to my cotangent? Larger, and we have to say something specific about it. These are getting larger. What else you can say about it that's important? They are negative, is that right? This is an axis. This is the origin of it. This is the positive direction. This is the negative direction. So what does that mean in your picture? It means once you pass 90, this is going to start to descend into negative territory. When does it become minus infinity? What angle should I have here so that that intersection is pushed all the way to the left? 180. This has to open completely. Then that intersection moves all the way to infinity. Like when you have a flashlight pointing to a wall, if you take your flashlight and make it parallel to the wall, you're going to light up very end of the wall, if there is such a thing. So at 180, yes, not going to show on the video, but at 180, this picture descends all the way to minus infinity. Okay, so I realize you're having a little bit of a hard time with this thing. This was the description of cotangent using unit circle. Secant and cosecant can be explained, but it's going to be a little bit more involved. So let me pass through that stage, answer your questions from 57 and 58, and next time we are going to talk about some of the identities and transformation of sine and cosine. 1/6 is going to be a bit more complicated than what we are doing right now, so make sure you study the text. So going to some questions you had. Here's question 57. That question is, comparatively speaking, is a little bit harder than the rest of them. So it's kind of icing on the cake. Make sure you do the basics, and then this is cherry on the top if you wish. Y equal to sine of x is given. The question is, use a graphing calculator, which we are not using, to determine the domain, range, period, and amplitude. Now, concept of amplitude we haven't talked about, but you can guess. Let me briefly introduce that and then we answer. So if you have a wave, any kind of a wave you might have, this wave has highs and lows. The distance between high and low can be divided into two, and you can introduce a so-called midline. Okay, from midline to either high or low is going to be your amplitude. So this one or this one is called, shown by A, and that is your amplitude. Period we have seen before. Period is how long you need to wait the shortest amount of time you need to wait for a picture to repeat itself. So that was the period of a function. So typically, one way to describe it is from one high to the next high for a simple wave. From one high to the next high is going to be your period. Or, if you want to use the intersection with the midline from this mid intersection, not to the next one necessarily, but you have to repeat the exact behavior of the function. Like this is going up, you have to go to the intersection where exact same thing happens. So from here to here is your period. So make sure you don't go from here to just the next intersection. That's not how it goes. It has to be an intersection that repeats the behavior. So from the high to high, or from low to low, or from an intersection to an intersection that shows the same behavior. What was the domain? Domain, the set of all acceptable x's. Those are the values that if you give to your calculator, it typically does not complain about them. Like if you're on calculator, you try to divide by 0, typically it nags at you by saying error, or shows E, or shows NaN, or shows, there could be a long list of complaints. It spits back at you, division by 0 perhaps it might say. So all x's for which we are going to get an ordinary number out of our operation, we call them the domain of, okay, whose range? If you take all of these x's, throw it to your function, and collect all the y's that come out of it, the description of all those y's is the description of your range. So set of all y values. That comes out of your function. Okay, now see, we have a couple of minutes. Sine of x, let's go remember what sine of x itself looked like. This was one period of sine, and the rest of it would be a block just identical to what we have drawn here. Question. We want to take this and square it. What does that mean, you want to square? What does it mean to square a picture? What it means is the following. Let's take one point of it and try it out for a good measure, and that's going to, suppose I take 30 degrees. At 30 degrees, my sine is a half. So I say, suppose, for example, x is 30 degrees. So sine of x becomes sine of 30 degrees, which is what? It's a half. Now, this is saying after you're all done with that, take that thing and square it. So what do I get when I square 1/2? We're having a bit of algebra problem, but 1/4, is that right? 1/2 squared, we don't multiply. This doesn't mean multiply, it means multiply by itself. So it's 1/2 times 1/2 makes a quarter. So if I take this number and square it, I come lower. Now suppose I come to this corner to see what happened. Suppose I come so close that this is 1/10. If I square it, what happens? 1/10 squared makes 100. So when I come close to the origin, when I square these things, they shrink, they kind of get stuck to the x-axis. Let's go to the other extreme. Suppose I come to this very high point. The high point, what's the height of this? Sine of x at its maximum, the height is 1. So if I square 1, what do I get? So here's the issue. At x equal to 90, sine of x is sine of 90, which is just 1. Now if I take that and square that one, what do I get? Just 1. So here are some points. This point goes here, this point goes here. Down here I realize that the red curve is getting squished. What do you mean squished? When you square these small number, they get substantially smaller. So the picture kind of looks like this. you need a calculator to get this thing accurately done. Right and left of this picture will be same. So whatever happened here is going to happen here as well. Now, interesting thing on this side. Suppose, let's go to this easy point. When I square this one, where do I go? What is the height at this point? No. What is this point? -1. When I square it, where do I go? 1. So, if a picture is below the x-axis, it's square, you square it, what happens to it? It flips on the top. It becomes positive because you're making it positive. -1, square it, it comes to +1. How about like at this point, if it was -1/2, when you square it, what happens? Becomes +1/4. So this bottom piece, when you square it, it flips on the top and repeats this picture. Okay, so we just talked our way to what's going to happen when you, so this is sine square of x. First of all, what is the range of it? What's the domain? All numbers. I have no problem finding sine of x at any point, and squaring it doesn't give me any headache either. Any x is fair game. That was easy. How about the range? Range is set of all kind of y's you get. How do I describe all the y's I get on this blue curve? I get all sorts of numbers from 0 to 1. Is that right? That blue curve never comes below, so I never get any negative. It doesn't go above 1. I don't get 2s and 3s. Range is all numbers from 0 to 1. What else do we want? Period. What is the period of this function, you think? Remember, we had several approaches to this. One of them was high to high or low to low. What does it look like? This low point to this low point, or this high point to this high point. These are indications of periods of this function. Well, what is the length from this point to that point? For the red one, from here to here was how many degrees? Yes. When you squared it, the period of it became half. So here's the period, 180 degrees. What else? Amplitude. What did we say about amplitude? Half the distance of high and low. Here's a high, here's a low. What's the amplitude? Midpoint of it is midline of this sine curve or cosine curve is here. Amplitude of it is the distance of the high from this midpoint, or this low from this midline. What are each of them? Half. Okay, now you can go to any of those websites I have put in your list of websites, and graph it and look at it again. Try to do 58 on your own. See, you can handle. Those are, again, problems at the very end of the scale. Make sure you do all the other ones, basic ones. And then all the discussion I had with respect to unit circle, you can find a more extended version of it on the last problem of this section. That would be problem 89. Good luck.